Sven, the floor is yours.
Thank you, Gerald. Maybe we can talk a little bit about an introduction to potentially all these presentations, certainly this one. One of the difficulties in trying to compare costs with what was done compared to what might have been done or would have been done as an alternative is that you never build something twice. And so this case history, we did not build anything twice, but we did design it 7 times. And we used actual production numbers to compare the cost of those 7 different designs. So the best we can do when we don't build it more than once is to design it more than once, and that's what this case history presents. Again, thank you all for attending, and we will jump right into this case history on how testing saved money on the driven pile foundation for a high-rise building. So here's the outline of what we'll be talking about. First, we'll talk a little bit about the project background, give you a sense of some of the details. There was a pre-production test program done, so we will discuss its scope and its results because it's those results on which the cost evaluation was based. And then we will look at the various construction control methods that might be employed on a project. And all that means is a construction control method is the means by which you establish driving criteria. How do you know when you're going to stop driving the pile? And that'll become clear. We arbitrarily assigned, or I should say, assigned some safety factors to various construction control methods so that we could put costs to them. And then we evaluated costs of those various allowable loads resulting from those safety factors, both with contribution from setup and without contribution from setup. And then we looked at the impacts, as Gerald just said, in terms of both cost and schedule. And the last point there, additional savings replacement piles, that gets toward the risk aspect of what Gerald just talked about a little bit. So again, as we think about cost, we need to think about both money and schedule and risk. So in terms of the soil profile on the site, the piles were driven from a basement level down here that's shown on this diagram. That was underlain by some lean clay. Again, not very stellar stuff, unconfined shear strengths rather, undrained shear strengths, 1,000 to 3,000 PSF, underlain by some fine grained granular materials, blow counts 15 to 30, again, not real stellar stuff. And below that, we got into a little denser fine grained material, silty sands, blow counts 25 to over 50 blows per foot. And we'll see with the pile lengths noted later that the piles stopped either at or slightly into this layer. This lower layer is actually a glacial till, extremely dense, but the piles didn't make it down there. They stopped again in this silty sand with the variable blow counts. So because it was a high-rise building, we knew that large or high allowable loads would match the column support requirements well. So we wanted, one of the objectives of the test program was to maximize the allowable loads that we could use on the project, but do it with a reasonable eye toward drivability. That is, piles that could be installed with reasonable equipment within the contractor's experience and availability at reasonable blow counts at reasonable stresses. So a 16 by ½ inch wall was selected for the test pile program and ultimately ended up being the production piles as well. These piles were backfilled with concrete, and both the steel and the concrete were counted on by the structural engineer for structural support. So for the test program and production driving, a D4632 was used that has a manufacturer's rated energy of 122 foot kips. So the test program, again, design phase, pre-production, included 10 total test piles, 5 indicator piles spread around the site to provide good coverage. And then there was a static load test performed, which had 1 static test and 4 reaction piles. And to optimize the cost effectiveness, the installations were driven fairly hard to maximize the end of drive capacity evidenced or available for the project. So that means to a reasonably high blow count and a reasonably high driving stress. We were trying to get the most out of the section that initial driving could evidence. And the test program included dynamic monitoring with a pile driving analyzer, full depth for all the test piles. Signal matching that consisted of CAPWAPs were performed on a representative end of drive blow for all the test piles. The test piles were restruck after a wait time of 36 to 54 days with a drop hammer. And because with GRL's Apple drop hammer, because they had set up and gained capacity, they needed to have a larger transferred force imparted to them to mobilize their geotechnical resistance. And so that hammer was configured to deliver up to 159 foot kips of transferred energy, again, greater than the initial drive hammer. So that was a test program. Let's take a look at what the results were. So a little review here. Recall that long-term capacity is the sum of two capacity components, initial capacity plus setup. And for those of you who may not be familiar, setup is time-dependent capacity gain after driving, most commonly associated with a full displacement pile like a closed-end pipe or a concrete pile or a timber pile. So again, review long-term capacity, two components, initial plus setup, and we'll be characterizing those two separately as part of the test program objectives. So here are the results from that preliminary or the pre-production test program. Driven hard, that section with that hammer, again, to reasonably high blow counts, reasonably high stresses, we felt like we could consistently evidence 800 kips end of drive. At a conservatively selected embedment length, in other words, the shortest embedment length we thought that the production piles might see, the test results indicated that we could expect about 400 kips in setup. In other words, 400 kips of capacity gain after driving. So that gave us a long-term ultimate capacity of 1,200 kips. That was what the long-term pile installations would be good for. That's what we could base our design on. So given the number of piles on this project, a full complete test program was performed as we just went through. Indicator piles, CAPWAP analyses on end of drive, dynamic monitoring results, restrikes with CAPWAPs, instrumented static load test program. We felt justified a safety factor of 2. So dividing that long-term 1,200 kips by 2 gave us an allowable load of 600 kips or 300 tons. And that's what the project proceeded with. It was driven and installed on 300-ton, 16 by half-inch piles. So the production results when the project was done were that there were 456 production piles installed to an average depth of 66.5 feet. So not too deep, not overly deep for attaining that kind of capacity. And those numbers will give you a sense of how that compares to your own projects in terms of number of piles and linear feet. As driven pile projects go, 450 piles really isn't a whole lot. So as we go forward and look at these savings, kind of keep these numbers in mind for relative comparisons to size of other projects. So now let's look at what it may have cost, the best we can estimate, put a quantified dollar amount to other design and testing scenarios if we had not done this full test program and been able to use a safety factor of 2, or if we had not characterized setup. So again, recall that with setup, we had a long-term capacity that the piles developed of 1,200 kips. So if we look at alternative options for construction control method, in other words, what may we have done differently than we did to establish driving criteria, we looked at various construction control methods and combinations of them. So DF is dynamic formula, WE is wave equation, DLT is dynamic load testing, that's with the pile driving analyzer, and SLT is static load testing. So from the bottom up now, increasing levels of testing, we have more information, more certainty in our results, better designs based on better information, if you will, less risk, and so the safety factor decreases. So as we apply these safety factors to this long-term capacity, we end up with this range of allowable loads. So this is what was done, the first row, full testing, low safety factor with a 600 kip allowable load. We were trying to get a handle on what would it cost had we not done that, if we had done other alternatives. And this table is not intended to recommend testing combinations of construction control methods or to associate specific safety factors with those combinations of construction control methods. It was just that to do the cost analysis, we had to put costs to representative testing that we felt may be associated with the range of allowable loads. The analysis really wanted to look at a range of allowable loads, and we wanted to assign reasonable testing costs to those. So please don't associate these construction control methods with recommended safety factors. So that's with setup. Without setup, recall that we would be restricted to 800 kips end of drive only, not counting on any capacity gain after driving. So if we take that same range of safety factors and apply it to 800 kips, we come up with these 4 allowable loads. So you can see that the 400 kip allowable load is repeated in these 2 tables. And so there were 7 different allowable loads, and this is what Adam did with the 7 different designs for the structure's foundation, actually designed it 7 times, including the pile count and pile cap volumes. And that's how we put costs to things. So another recognition here is and thank you, is the cooperation of the construction manager and the pile driving contractor and the ownership team for providing the costs and other parameters that allowed us to put numbers to these various scenarios. So this slide will illustrate our assumptions in putting together those cost and schedule impacts, but that came from the design and construction team. And again, a big thank you to them for their candor in providing this information. So for an installed pile cost, $51 per ton was used. That includes both the steel shell and the concrete fill. For the cost of the pile caps, 2 different prices were used. $565 per cubic yard for the caps themselves, which were isolated and smaller, and a lower unit price was able to be applied to the core mat, which was underneath the elevator and foundation in the central part of the building. It was a larger excavation, and so had a lower unit cost. Those are the numbers that were put to the concrete costs that you'll see later. And then the construction control methods were, again, actual numbers based on numbers from both the contractor and the engineering team, the geotechnical engineering team. And so when we look at testing costs, engineering costs are included in that. So if a construction control method includes field testing, like dynamic testing or static load testing, the cost that will be reported for that also includes any office time with the coordination or analysis of that field testing. And when we look at schedule impacts, the backed out driving productivity, the full driving schedule for the production piles divided by the number of piles worked out to 5.4 piles per day. Now, some of you may look at that and say that's not much of a production rate, especially considering how short the piles were, but it was an extremely tight site. Recall they were driving in a basement. They had to relocate and reconstruct the access ramp to several places within the basement several times. So it was more, this productivity is more site constraint driven than contractor productivity or means and methods driven. So that sets up what the whole purpose of the exercise was, the case history look, and that is to look at the impact of costs and schedule and risk. So let's look first at cost. This is with setup. So we're starting with 1,200 kips long-term. And we've seen these first 3 columns before, the construction control methods, an assigned safety factor that goes with them, and then the resulting allowable load dividing the long-term capacity of 1,200 kips by the safety factor. What's new on this slide is the pile count, and you can see that it obviously increases with increasing safety factor and decreasing allowable load. That's not a surprise. The total foundation cost is listed in the far right column, and again, that includes the cost of the piles, the pile caps, the core mat, the construction control method, which includes the engineering. So you can see that these increase with decreasing allowable load. That's kind of to be expected because the pile count goes up. And again, this is assuming that all the piles are driven to the same length as the actual production piles were driven, developing the same capacity, just dividing by a different safety factor, again, depending on the testing that was done. And as Gerald alluded to in his opening remarks, everyone on a project is extremely aware of and sensitive to the cost of testing, but the benefits are often hidden and not as easily quantified. The analogy I use is the changing oil in your car. It's very easy, your car or truck, very easy to quantify the cost of preventative maintenance. It's very hard to quantify the benefit of preventative maintenance. And so that's the whole purpose of this case history, is to try to put some numbers to that so that it's not just, say, hand waving or guessing that increased testing saves money, but to actually quantify it. And you can see here that even including the cost of the testing, the most aggressive testing, most expensive testing program actually had a foundation total cost that was less than any lesser testing efforts. So if we then did the same exercise without setup, in other words, we aren't going to do restrikes, we're just going to drive the piles, run the static load test as soon as we can after they're driven, and not characterize setup, these are the numbers. And you can see the pile counts go up significantly because the allowable loads go down significantly. And again, the cost of the foundation with the full testing, with as much testing as we did, is still the least expensive. So let's break out the contribution of the setup individually. So this table represents how much savings there was from testing for and characterizing and incorporating into the driving criteria setup on the site. And by the way, the 400 kip contribution to 1,200 kips long-term is 33% of the long-term capacity, a doubling of the initial capacity, or 50% of the initial capacity. That's in the middle to, you could say, maybe on the low end of what might be measured in some areas for setup. Setup contribution may be higher than what is shown in this case history. These were predominantly end-bearing piles, and with friction or shaft resistance piles, that setup contribution may be a higher percentage. So these numbers may underrepresent the setup contribution in some soil conditions. So again, these now are, when it says pile count, that's the number of piles that was saved by characterizing setup. And the same thing with the construction control costs. That's how much was spent extra to characterize the setup. And you can see that it was not an inexpensive effort to characterize the setup. And yet, even with those kind of expenditures, the overall savings from characterizing setup more than exceeded the cost of testing. Extremely cost efficient to test for setup and incorporate it. This gives us a sense of how allowable load selection affects foundation costs. So on the vertical axis, we have constructed foundation cost, and on the horizontal axis, we have allowable pile load. And again, the purpose here is to show the effect of various allowable loads and allowable load selection, which is a variable that's available to the designer. The soil conditions are fixed, the building loads are fixed, the soil response to driven piles and how they set up and the capacities they make at what depths, that's all fixed. But the designer has at their option the selection of allowable pile load. So this kind of gives an indication of the effect or the benefit of doing that judiciously. So these numbers simply represent the ranges of these various parameters that were realized by the ranges of the allowable loads selection. So over the total differences in allowable loads, these were the differences evidenced by the case history analysis. And you can see that, for instance, the total cost of the foundation is significant over that range of allowable loads. So there's a couple of things to be drawn from this plot as well. One is that the piles themselves, the material costs of the pile and steel, is really the largest component of a driven pile installation, is the material costs, not the labor or the mob or the driving time. But I think that a lot of us in the industry already recognize that. The other thing that comes out of this is that it's a law of diminishing returns. In other words, small increases in allowable loads yield large benefits in cost savings, particularly at the low end of the range of allowable loads. In other words, you don't have to target huge allowable loads. You don't have to push the envelope, so to speak. But small increases, especially down in the lower allowable load range, result in significant reduction in foundation cost. So it's certainly worth thinking about increasing allowable loads, using higher allowable loads where the structure support requirements warrant it, where the column loads are high enough to justify it. So that's sort of the quantitative look, if you will, at the impact of cost to various construction control methods, testing levels of effort, the cost associated with them, and the foundation design ultimately. Then let's take a look at the impact on schedule. Very similar look. Again, we're starting here with a 1200 kip long-term installation. That's with setup included. We've seen these columns before, and now it's added here is the driving duration based on our productivity rate and the number of piles, or the pile count for the project. And again, you can see that more testing is now saving schedule. And as Gerald said, schedule has costs. There's the contracting costs themselves, but there's also opportunity cost to the facility being opened and generating revenue. There's also maybe opportunity cost to the loans or any other monies that are out waiting for the project to be opened and repaid. So again, just an indication and a quantification of how the testing saves schedule as well. So if setup were not included in the testing program, and we started with an 800 kip ultimate end of drive capacity and divided by the various safety factors, we'd have these driving days duration. And again, more testing and you get your lowest number of driving days. So, sorry, went the wrong way. This then quantifies the savings in schedule from having characterized the setup. And you'll notice that with this full program, the savings in schedule days is the least with doing the most testing, but it's more than the testing took to characterize the setup. In other words, when you hear someone automatically say, we don't have time to test for setup, a reasonable question is, well, does testing for setup save more time than it takes? And the other corollary to that is that setup comes on very quickly after driving, and then its rate of increase diminishes with longer times after driving. So using short restrike times can characterize a fair amount of setup and not punch a big hole in the schedule. So I would caution you and encourage you to not have a knee-jerk reaction that we don't have time to test for setup, when in fact testing for it might actually decrease the overall project schedule. And a similar plot showing, again, vertical axis, now we have duration, pile driving duration on calendar days, horizontal axis allowable pile load, and decreasing with higher allowable load is the driving schedule. And again, we see that the largest benefits are from increases in relatively low allowable loads, and then you have a law of diminishing returns in terms of schedule benefit savings with higher and higher allowable loads. So again, small increases, low in the range, big benefits. This is a component of test programs that's often overlooked, a benefit, a potential savings, and that is that how the information from test programs can be used to address production pile driving issues. So let's take a look at, for this particular project, how the test program results were used and applied to the requirement for replacement piles. Now, a reasonable question would be, hey, if you're driving these piles to fairly high blow counts and fairly high stresses to maximize their end of drive capacity, wouldn't that lead to increased risk for damage and mortality? And so we quantified that. And the number of production piles damaged during driving was approximately 3%. And so this following review process was developed to look at those 3%. The first thing we did was to assign shaft resistance above the damaged location. So if the pile's toe was crushed or if it was dimpled or collapsed, we took the shaft resistance from setup only and applied that above the damaged location to give the pile a much reduced capacity, but at least give it some credit for capacity, set up above the damaged location. Then we looked at the driving records for other piles in the cap on an individual basis and assigned an individual capacity to them. And sometimes that was higher than their allowable load, because say you're looking for 30 blows a foot, maybe you get 45 blows a foot. Well, you go into the wave equation and you come out with a slightly higher allowable load and assign it to that pile, and again, including setup down to that depth. We transmitted that information to the structural engineer, who then looked at what did the cap really need for support. You know, if you divide a column load by an allowable pile load and you require 5.4 piles, you don't install a 0.4 of a pile, you install 6 piles. So maybe the cap had excess capacity to begin with, or maybe the damaged pile is near the center of the cap, near the neutral plane, and neutral axis, and maybe that interior pile doesn't need as much capacity as, say, an exterior pile on an edge where bending moments come into play. So the structural engineer looked at all those things and determined the need for a replacement pile. And I hope some of you are thinking, well, if it's a tight site and they have nowhere to go, they really don't have time to sit around and wait while 2 engineers evaluate all these things. Well, we got this system down to where if we received a driving record from the field of a damaged pile, we could get an answer back to the field in about 15 to 20 minutes. We streamlined the operation, use of spreadsheets and very efficient looks at things, communication between the geotech and the structural. It was a very quick turnaround, and there was no holdup. So using the test data to reduce the number of replacement piles saved 50% of the required replacement piles had we simply tossed them, given them no credit for capacity, which resulted in a savings of $70,000 and 3 calendar days of driving. So in conclusion, the savings from testing exceeded the cost of testing. The savings for incorporating these setup exceeded the cost of testing for setup. The time required to test for setup saved more than more time than it took to test for setup. And the results were of additional value during production driving. So this case history is presented in more detail in a paper. It can be found on GRL's website. At this location, you can go to GRL's website, look under resources, and do a search by my name. It was also an article in Pile Driver magazine, the issue and years listed there, and that article has an interesting sidebar commentary by the structural engineer. So we offer that for your your further reading if you're interested in more detail. So in conclusion, I hope we've demonstrated and given you some ammunition. Hopefully this is a quantitative demonstration or convincing tool that you can take to teams and show them that it's not just talk to say increased testing saves money. It can be demonstrated quantitatively. So with that, I thank you and turn it back over to Gerald.
Thanks, Ren, for your very interesting presentation.